chapter 21 is a bunch of detailed things about hypothesis tests and confidence intervals. All right. So this was a separate chapter as to not overload you about hypothesis tests in general. All right. I'm not changing hypothesis tests, so don't freak out. I'm just going to give you some more information. So I'm going to give you a lot of that information today and then a little bit more tomorrow. But the first few things we're talking about, it's going to all seem to feel like segmented stuff. It's all related to hypothesis tests, though. So it's just going to be like one topic, another topic, another topic. Okay? Again, the confidence intervals and hypothesis tests are not going away. The general idea and general steps to them are staying the same. And in every chapter after this one, for the rest of the year, we talk about a confidence interval and a hypothesis test or some other type of data. Okay? So generally, whatever, the only thing that changes is the mechanics. And then the hypotheses, because you're not talking about proportions anymore. Okay? So you have to be able to figure out, okay, what kind of information am I picking out? Like, what kind of information do I have? So you can pick out what kind of interval or test you're supposed to do, and then go through it. So all that stuff is still important. So this is not the time of the year where you learn something and you forget it. That would be bad. All right. So first thing in chapter 21, we've already kind of talked about in chapter 20, and some of you guys had it, but some of you don't. And it'll come up on an AP exam somewhere, and it should be easy points, and then you forget. So the first thing is, again, what a p-value is in general. Not how to write a conclusion. You guys can write a conclusion to a hypothesis test. That's fine. You can say high, low, fail to reject, context. Done. But what does that percentage, what does that p-value really mean? We talked about this in chapter 20. We'll talk about it again. It tells you the probability of getting results at least as unusual as the observed statistic given that the null hypothesis is true. During a hypothesis test, you're assuming the null hypothesis is true the entire time. That is why you use that value for every single condition and anything you have to calculate, right, except for in the z-square. So everything else is based on that null p-value, or null p, so we're assuming the null hypothesis is true. So I'm making up examples. We'll look at one in a second. On one of your quiz corrections for some chapter, maybe, I don't know if it was 19 or I don't know, it talked about nearsightedness in kindergartners. All right, so I'm going to make some numbers up. Let's say we think that nearsightedness in kindergartners is increasing. All right, we would do a hypothesis test because they gave us information, and our alternative would be that p is greater than whatever we thought it was originally because it's increasing. We get a p-value of 0.08. You guys can write the conclusion. 0.08 is high, so we fail to reject, and you write that in context. That means we don't think there's an increase in nearsightedness in kindergartners, right? But what does that 8% mean? Well, that 8% means that there is an 8% chance that we would get results similar to what we had in our sample if the null hypothesis is true, if p was really whatever it said on the problem. Okay? You need to be able to answer that. It'll show up in a free response, or they'll ask you a multiple choice question about it. Just make sure you know that. It would be like 8% chance that we would get results similar to what happened in our sample. So similar proportion is what we got in our sample, in this case, given that the null hypothesis is true, or assuming the null hypothesis is true. Right, so it's a probability about your sample data. It is not a probability about the null hypothesis. You use the p-value to reject or fail to reject, but it is not the probability that the null hypothesis is true. Not it. Okay? So there's not like an 8% chance that kindergartners are nearsighted blank percent of the time, whatever the p-value, p was in the hypothesis. Okay, so not that. It's the probability that we're going to get your sample data again if the null hypothesis is true. Does that make sense? Let's look at a question. We talked about the actual question a few chapters ago, but it says, after the political ad campaign described in Exercise 1A, pollsters check the governor's negatives. They test the hypothesis that the ads produced no change against the alternative, that the negatives are now below 30%. So P equals 0.3, and P is less than 0.3. They found a p-value of 0.22. Which conclusion is appropriate? And explain. So it's asking you which one of these is the correct interpretation of what a p-value is. So A says there's a 22% chance that the ads worked. This is not what we're talking about. All right? That's saying there's a 22% chance that the alternative hypothesis is true. It's not about a hypothesis. B says there's a 78% chance that the ads worked. Again, that is about a hypothesis, and that's just, that's 78 doing 100 minus 22. But again, it's not about a hypothesis. C is there's a 22% chance that their poll is correct. I don't really even know what that means. I don't know how a poll can be correct. There's a valid sampling strategy, or there's a valid method for calling people, but there's not like the poll is correct. I don't know what that means. So D is a correct interpretation of the p-value. There's a 22% chance that natural sampling variation could produce poll results like these if there's really no change in public opinion, if the null hypothesis is true, that there was no change in public opinion. Right? That is what the p-value should be. On the homework tonight, that's what you're going to practice at the beginning, is how to write a p-value. Do you have to have it as wordy as this? No. But that's what it's saying. 22% chance that we could produce a sample that had similar results if there's really no change in public opinion, if the null hypothesis is true. Questions about p-values? This is the second time we've talked about them. Again, it's just going to come up. It'll show up on a free response, and you don't want to miss that part just because you forgot what it is. Question? All right, second topic today, alpha levels. You actually already know what an alpha level is. I just didn't call it this. So, when we do a hypothesis test, you get a p-value, and you have to decide if it's high or low. In order to decide if it's high or low, you have to have some sort of threshold, right? I told you in this class so far, just use 0.05 as your threshold. Well, the threshold is called an alpha level or a significance level. Okay? So if they said complete a hypothesis test and use an alpha level of 0.05, that's exactly what you've been doing. If your p-value is higher than 0.05, you reject it, or fail to reject. And if it was less than 0.05, you reject it, right? So you've already been doing that, just as a fancy name. Other common alpha levels are 10% and 1%. If they don't give you one, then you just state what alpha level you used in your question. All right? So from now on, you should write at the end of your test with a p-value higher than 0.05 or less than 0.05, or if they tell you it's 0.01, higher than 0.01 or less than 0.01. You want to reference the alpha level in your conclusion. All right? So it's not just high or low arbitrarily. It's high or low based on an alpha level. Again, it's also called a significance level. So make sure you know those two terms. They should give you one. Again, if they don't, then you need to state what you used. It depends on the context of the question about why they would use a different alpha level. If they're dealing with something that really doesn't matter in the grand scheme of things, like it's not a life or death conclusion, then they might use 10%. Now, if you use 10% as your alpha level, you're giving yourself more space to reject, right? So maybe that's good for you. I don't know. But if you're dealing with, like, a lot of this comes up with, if you're dealing with medicine, right? You're doing some sort of drug trial, okay? And you're trying to see if this new drug is better than the old drug or something. Well, you probably don't want to use 10% to reject. That's like could be a life and death scenario if you approve this new drug or not, okay? If you approve a new drug and it's really not good for people, then it's probably a bad thing. So a lot of the time in drug trials, that kind of stuff, you use 1%. You give yourself less of a chance to reject and fail to reject, right? You give yourself 1% chance to reject, and that's it. So it depends on the context, depends on what they're going to give you. And if they don't give you one, you need to assign one for the problem. It's not wrong to assign 0.05. That's why I told you use that threshold in chapter 20. Any questions about that? Excellent. Yeah. Okay. Going along with that, third concept today, significance versus importance. When we reject a hypothesis, your p-value is low and you reject something, we say it is statistically significant. All right? But just because something's statistically significant does not mean that it's important. I'm going to do an example in a second that would explain why. All right? But so if you reject, you have a statistically significant result because you rejected. And then sometimes you have to go back and think about if that's important in the context. Would you really make a change because of this result or not? Just because you rejected doesn't mean you have to do anything, right? So here's why I'm saying this is a big deal. Public health officials believe that 90% of children have been vaccinated against measles. A random survey of medical records at many schools across the country found that among more than 13,000 children, only 89.4% had been vaccinated. A statistician would reject the 90% hypothesis with a p-value of 0.011. Explain what the p-value means in this context. So that's practically what we did earlier. So there's a 1.1% chance that we could get similar results in a different sample, given that 90% of children had the measles vaccination, or given that there wasn't a change in the amount of kids that had measles vaccination. Okay? Practicing context and what p-value is. And it says, B, the result is statistically significant because we would have rejected. It says they would reject p-value 0.011. We would reject the null hypothesis. But is it important? So, if you are in charge of public health, and let's say you're looking into this whole measles vaccination thing because there's been a measles outbreak or something in just the nation or something, and you're trying to decide if you're going to spend funding to educate more people about the measles vaccination, something, okay? If 90%, you think 90% are getting vaccinated, and really 89.4% are getting vaccinated in your sample, even though we have a statistically significant result, is that 0.6% difference enough for you to spend public money or whatever to start a big campaign? But probably not, right? If you're really looking at budgets and stuff, you probably aren't going to start some big deal over 0.6%. So the result here might not be important, even though it was statistically significant. Does that make sense? Yes. Now, maybe that 0.6% difference is big enough deal because measles, we don't have people with measles, blah, 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 right? But just that's where significance versus importance. Yes, it was statistically significant. Is that result important? Depends on what position you're in and what you have to, like what you're trying to decide to do. Does that make sense? Okay. So I moved a slide just now. Right there. All right, next little tidbit. Confidence intervals as hypothesis tests. If you're given a scenario on the AP exam, they will generally tell you to do a confidence interval if they want you to do a confidence interval. They will not tell you to do a hypothesis test. You've seen it already on free response we've done in class and on quizzes and on tests. It just asks the question, is there evidence that something happened? If it says, is there evidence that, that's like code for complete a hypothesis test. Now, if you're given the option, for whatever reason, and you have enough information to do a confidence interval or a hypothesis test, you should always do a hypothesis test. I'm going to tell you they're better, right? A confidence interval is based on an estimate, and it gives you an interval, and it's kind of wishy-washy, because then you're like, I'm this % confident that P is in here somewhere. Whereas a hypothesis test, you get a probability at the end, and you can make a definitive conclusion based on that probability. Okay? So I'm going to tell you a hypothesis test is better every time. Now, you can do a confidence interval in place of a hypothesis test. So let's say they don't give you enough information to do a hypothesis test, but you need to make some sort of conclusion. You can complete a confidence interval, and once you complete the confidence interval, if you had hypotheses, you could see if that interfell like below one of your hypotheses or above one of your hypotheses to see if it was increasing or decreasing. But you need to have some sort of threshold about where you would make a conclusion in your hypothesis test. So that's where I'm going with it. So they have the same conditions and generally the same setup, and they're based on similar sampling distributions, so it's okay that these are related. And it says because confidence intervals are naturally two-sided. Why would they say confidence intervals are naturally two-sided? Right, there's a plus minus, right? You have a range. Okay, so naturally two-sided. So they correspond to two-sided tests. A two-sided test is when you had not equal to as your alternative hypothesis. Okay? So for example, a 95% confidence interval corresponds to a two-sided hypothesis test at alpha equals 5%. Generally, your alpha level is 100 minus whatever your confidence level is. So you have this confidence interval, and then you can make some sort of conclusion. We'll do an example in a second. And then they're going to ask you, well, what significance level would you have used? Well, it's 100 minus your confidence level. But what if your alternative hypothesis was not equals to? It was greater than or less than, like most of them have been. If you have a one-sided alternative, then what's going to happen to your alpha level? Right now, this is a two-sided alternative. So how do I find the alpha level for a one-sided alternative? You multiply by 2, now you have a four-sided alternative. That doesn't exist. Divide it by 2. Right, you take a two-sided alternative and you have a one-sided alternative. So if the alternative hypothesis had been like greater than something, and you had a 95% confidence interval, you would do 100 minus 95 and get 5%. Divide by 2. Your alpha level is 2.5%. Okay? Yeah? Let me do an example about how that works real fast. And so you can see how a confidence interval could be used to make a conclusion. In August 2004, Time magazine reported the results of a random telephone poll commissioned by the Spike Network. Of the 1,302 men who responded, only 39 said that their most important measure of success was their work. So A says estimate the percentage of all American males who measure success primarily from their work. Use a 98% confidence interval. Check the conditions first. Okay, so I'm not going to write all the conditions down because I don't want to do that. If you guys don't know the conditions by now, you haven't been paying any attention. So you have to check all of your conditions. I've already checked them all. It's good to go. All right. So we're good. We can do a 1 proportion Z interval. And if we're going to make a conclusion, we can then do a Z test. All right. So for the Z interval, if you're going to write it out, you have P hat plus or minus Z critical value times the standard error. So P hat is 39 out of 1,302, and that ends up being 0.03. And how am I going to find the critical value? Yeah, how am I going to find that? Right, inverse number 0.01, because we take 100 minus 98, there's 0.02 left. We divide it by 2 sides, because we need one side, so 0.01. And I already did that. I'm trying to save us time. You get 2.33. Everyone trusts my math, but I'm trying to say, you guys know how to do confidence interval. So here's your interval. We would then need to write the sentence, I'm 98% confident that the true percentage of all American males who measure success primarily from their work is between 1.9% and 4.1%. Yeah? So that's part A. Now, part B says, some believe that few contemporary men judge their success primarily by their work. Suppose we wish to conduct a hypothesis test to see if the fraction has fallen below the 5% mark. What does your confidence interval indicate, and explain? So for this, we would need hypotheses. They want to know if this percentage has fallen below 5%, which means our original percentage is 5%, and our alternative is that P is less than 5%. So if you're looking at this interval, you have 1.9% to 4.1%. That entire interval is less than 5%, right? There's no overlapping. I mean, it's entirely below 5%. That seems like sufficient evidence that we could reject the null hypothesis, right? It seems like it has fallen below the 5% mark. All right, so we can make a conclusion. We could say 5% does not lie within the interval. It falls above the interval, so it seems like it has declined. All right? Kind of like we do with the hypothesis test at the end. But then C is going to say, what is the level of significance of this test? Because we didn't actually do a test. All right, so we did a confidence interval in its place. So if you were going to do a test, how would I find the alpha level? Right. You always do 100 minus your confidence level. If this was a two-sided test, we would have left it. It was a one-sided test, so we divide it by 2. So our alpha level is just 0.01 or 1%. Everyone happy with that? Okay? We just talked about that. You can just say that it's a one-tailed test. So we would need to have half of that alpha level. So 1% alpha level will be used. Nothing really specific. But so you could confidence interval to make a conclusion. Again, if you had the information available to you, I would always do a hypothesis test if you could. Questions about that? All right. Then one more thing, and this is the big thing for the day. Like everything else is like kind of like a mini little piece of information that kind of need to be thrown out there for you. But this is big. Really big. Errors. When you complete a hypothesis test, you make a conclusion. Is there any way to guarantee that your conclusion is correct? You just base it on a probability at the end, right? And that probability is all based on one sample that you did. And we know enough about sampling that if we do one sample, anything can happen in one sample, right? So maybe you do one sample, and it's like a wackadoo example, like sample. And so you get crazy results, and then you reject at the end based on this wackadoo sample, okay? So you have to understand that even though you do a hypothesis test, you've done all the math right, and you make your conclusion is not necessarily correct. All right? There are two types of errors you can make. They don't have great names to help you remember which one's which. They're called type 1 errors and type 2 errors. All right? But it's your responsibility to know which one is which. Okay? So, type 1 errors are when the null hypothesis is true, but you reject it. Mistakenly is misleading. You reject it because that's what your hypothesis test says to do at the end, because you're a p-value. That's what you think you're supposed to do. That's why it says mistakenly. But in actuality, that's not what it's supposed to happen. In a type 2 error, the null hypothesis is false, but you failed to reject it. Again, there is no way of knowing if you make these errors unless it comes back and tells you, like in the problem, oh yeah, by the way. But like in real life, there is no way for you to know if you make an error or not. So you have to be okay with the fact that you could be making an error. That's why people use different alpha levels. We'll get into that in a second. Now, this is where this is so big. Pretty much every single free response, not every single free response question, a lot of free response questions, a lot of multiple choice questions, they're going to ask you about errors. All right? They're going to say, here's some stuff for the hypothesis test. Which one of these is a type 1 error? Or what's the ramifications of a type 1 error? Right? You should know what a type 1 error is then. All right? Pretty much this doesn't go away this is not just for this type of hypothesis test, one proportion z-test. This is for any test we do the rest of the year. You can make these errors. They're very generic. Okay? So you have to know that they're happening. What's going to happen, what they're going to ask you to do generally, they're going to ask you to do one of like 4 things. They're going to ask you to write one of the errors, type 1 or type 2. They're going to ask you to write both of the errors. They're going to ask you to tell what the ramifications are for one of the errors, or what the ramifications are for both the errors, or what population would that error be a detriment to, something along those lines. All right? And we'll get into more tomorrow about some probabilities that go along with these errors. So, this is the best the book can do about helping you memorize which one's which. I don't think it's very helpful, so I just got to memorize it. But it says one way to keep the name straight is to remember that we start by assuming the null hypothesis is true. So a type 1 error is the first kind of error you could make. That was not helpful to me. I'm not going to remember that. So if that's helpful to you, excellent. Okay? Now, some people like to do this written out. Some people like to look at it in table form. I am like in the camp that likes to see it written out, but you might be in the camp that likes to see it in table form, so I'll show you in table form what's happening. If you make a nice little table, right, it's almost like a nice little Punnett square. You have the truth, and you have your decision. Okay? So, if the truth is that the null hypothesis is true, and you reject that null hypothesis, but it's really true, you've made a type 1 error. If the null hypothesis is true and you fail to reject like you're supposed to, then that's what you're supposed to do, and that's great. Wonderful. If the null hypothesis is false and you reject, that's what you're supposed to do. Awesome. But if the null hypothesis is false and you fail to reject, you've committed a type 2 error. So if you set this up every time just like this, you'd have type 1 in the top left and type 2 in the bottom right. So some people answer the questions by making the table, and that's fine. I'm going to give you a worksheet in a second that has it both ways, written out and in the table. Let's do one more thing to go along with that. So how often will a type 1 error occur? Right? It happens when the null hypothesis is true, but we had the bad luck to draw an unusual sample. So to reject the null hypothesis, the p-value must fall below that alpha level, right? Well, so the alpha level is the probability of making a type 1 error. If your threshold is 5%, there's a 5% chance you're going to make a type 1 error. If your alpha level is 10%, there's a 10% chance you're going to make a type 1 error. If your alpha level is 1%, there's a 1% chance you're going to make a type 1 error. Again, this is why we go back and we talk about why you would select a specific alpha level. I talked about medical reasons a second ago. We talked about pills and stuff, and you're trying to approve something new. If you're trying to approve some new pill, then you want the probability of making an error to be very slim, a type 1 error. So you would make your alpha level as small as you could. Okay? Again, if it wasn't a life-threatening or life-and-death situation, then your alpha level could be 10%, and it wouldn't matter. Okay? But so your alpha level is the probability of getting a type 1 error. Those are the same thing. The probability of getting a type 2 error is a little more complicated, and we'll talk about that tomorrow. Okay? But it is important to know that type 1 error and alpha are the same. We're going to do a question real fast. So, right here. If you're trying to reduce the probability of any error at all, the only way to do that is to collect more evidence. You can't just like change one little thing and have a less probability of getting a type 1 error. You have to just take a larger sample. The larger your sample, the less likely it is it's going to be a wackadoo sample, and so then you're less likely to make an error. All right, here we go. A clean air standard requires that vehicle exhaust emissions not exceed specified limits for various pollutants. Many states require that cars be tested annually to be sure they meet these standards. Suppose state regulators double-check a random sample of cars that a suspect repair shop has certified as okay. They will revoke the shop's license if they find significant evidence that the shop is certifying vehicles that do not meet standards. A says, in the context what's a type 1, and B what's a type 2. In order to write those, you need to have hypotheses. If you're ever talking about errors, you need to write your hypotheses in context, not just in symbols, so you know what you're talking about. In this case, they don't even give you any numbers, so you have no choice. You have to write them in context. You can't write P equals or P is less than. Okay? So, in this scenario, your null hypothesis is always that nothing is happening. Right? Nothing has changed, nothing is happening. So in this case, the null hypothesis is the shop is meeting the state criteria. In other words, they're doing what they're supposed to do. Right? They are certifying cars they're supposed to, and then they are like docking those cars and telling them what they need to fix if they are emitting too many pollutants. Okay, they're doing what they're supposed to. Everyone go with that. The alternative would be that the shop is not meeting the criteria. So maybe they're certifying vehicles they shouldn't be. Right? Maybe something weird is happening at the shop. It's a suspect shop anyway, that's why we're doing this random sample on the shop. Okay? So, a type 1 error is when the null hypothesis is true, but you reject it. You have to write that in context. So, the null hypothesis is true. The shop is, in fact, meeting the state criteria. All right? So it's doing what it's supposed to do. Everyone go with that. But the state regulators claim they are not. Okay, so the null hypothesis is true. In actuality, the shop is doing everything it's supposed to. But you reject that claim, so you think that, so the state regulators came in and they said, nada, you're messing this up. Does that make sense? You've got to follow that sentence. You have to know those sentences. For a type 2, that's when the null hypothesis is false, but you fail to reject it. So if the null hypothesis is false, that means you're going with the alternative. So the shop is not meeting the state criteria. So they're doing some shady business. But you failed to reject it. You failed to reject the null hypothesis. So the state regulators claim they are. The state regulators are like, hey, everything's great here. Go about your business. All right? So when you're talking about errors, that's what it's always going to be in context. You need to have some hypotheses, and then you should know those sentences. Type 1, the null hypothesis is true, but you reject it. Type 2, the null hypothesis is false, but you fail to reject it. Now, it's going to ask you all ramifications. C, which type of error would the shop's owner consider more serious? So if you were the shop owner, which of these errors is worse for you? Number 1, right? Because you're doing everything you're supposed to, and they said you aren't, and they're going to revoke your license, and that's just rude. All right, so type 1 would be more serious for the owner. Now on D, which type of error might environmentalists consider more serious? type 2, right? Because the shop is not meeting the criteria. They're passing through cars that have all these emissions problems, right? And the state says they're doing everything fine. So now you have all these cars with emission problems. So the type 2 is going to be worse for environmentalists, right? Now sometimes, not really in this question, but sometimes you can get into a debate about which error is really worse, okay? Like which one is really that bad. In this case, they're both kind of bad. Okay, you revoke the license from the owner, or if you're an environmentalist, like, okay, this is a big deal because now you have all these emissions issues. Both of those are kind of a big problem. Sometimes you get into errors, though, that some errors are like kind of petty, and you're like, type 1 is way worse, all right? Or type 2 is way worse. And so you take that into account. If type 1 isn't that bad, then maybe your alpha level could have been bigger and it's not a big deal, okay? So it's important to think what those errors might be when you're setting those things up, okay? Does this make sense, this error business? It's not going away. It'll stay here forever, and I'm going to keep asking you about it. I know. Don't forget that chapter 21, you're not having a quiz over by itself. It'll be chapter 21 and 22 quiz together, combined. There's one more piece of chapter 21 we're going to talk about tomorrow. All right.